We're going to continue with the next section on structure preserving cryptography. We have the first talk on structure preserving cryptography analysis by Dennis Hofheims, Christina Hosakova, Roman Landwehr, and Dr.
Thank you for the introduction, Hendrik. Okay, so let's start. What is structure preserving cryptography? Historically, this is really related to the Grotzer-Hain NISIC, and at a very, very high level, because I do not want to define the Grotzer-Hain relation. The GS08 NISIC allows us to efficiently prove quadratic relations over the group elements of a binary pairing group and its exponents. It's more complicated than that, but for the purposes of this talk, this is enough. The main takeaway there was that the structure of signatures and encryptions in pairing groups, they're very compatible with these quadratic relations. And that led to a synergy between them, which was known as structure preserving cryptography. Again, at a very high level, what structure preserving cryptography allows is to prove two kinds of statements. You can prove that the ciphertext encrypts a valid signature, and you can prove that the signature signs a valid ciphertext. The second is far more easy because, well, the ciphertext becomes public when it's part of the signature. So we're going to focus on the first, and we're going to get the second one as we move on. And some other important properties of the GS of the Grotzer-Hain NISIC is that it's in the standard model, has perfect correctness. And what this means is that you can have these chains of encryptions and signatures. There's no loss, so you can like chain them forever. And because it's in the standard model, you don't have to worry about making proofs about a proof that has potentially some random oracle queries inside, which would be problematic. So that's why I mentioned that. And another interesting thing is that the Grotzer-Hain is really already tailored for the pairing, for a very pairing-like relation. And this means that it kind of allows native arithmetic. And it avoids, in this way, generic NISICs and expensive circuits. Well, that is very nice, but what is it used for? Here I put some examples of constructions that are enabled or enhanced by structure preserving primitives, and this is like verifiable encrypted signatures, delegated by anonymous credentials, group signatures, and weak signatures. And the question that we are tackling in this paper is, can we get structure preserving cryptography for lattices? And this problem is it hasn't been tackled before. What we do in this paper is that we formalize several unifying notions shared by a family of encryption and signature schemes. So we try to abstract out what is it needed from them in order to be compatible with each other. We provide a NISIC that is compatible with the notions that we extract, and we also have standard model security. This is our focus. Because again, the end goal for structure preserving cryptography should always be that you can have these like chains of like encryption signatures and so on without the boundary. So I'm going to go from example to abstract. And we're going to start with a regular encryption. So to recap quickly, we have a uniform matrix, a uniform secret vector, and an error. And we compute the public key, which is the matrix, and then this vector x, which is just the inner product of the secret of the matrix plus the error. In order to encrypt, we're just going to sample a vector that has coordinates -1, -1, 0, 1. And we're going to compute a times z and x times z plus a constant times the message. Now, in order to decrypt, we're not going to spend too much time on this, but basically, just multiply the first vector with s, use the transform C1, and these two terms disappear, and then you are left with some noisiness next to the message, so you can do the rounding operation. These are the dimensions that we don't have time to talk about them. So now let's do the same for Boolean signature. Let's do like a short recap. Here we have a matrix A, a short chapter for it. We are sampling L+1 matrices, C0 to CL. These are going to be part of the verification key. And the chapter is going to be our secret key. In order to sign, we first compute this C matrix, where we select, depending on which bits of the message are 1 or 0, we're going to pick some elements of the verification key. That's how we get the C matrix. Then we're going to concatenate it with A, for which I have a chapter in order to get the F matrix. And then we're going to use this trapdoor in order to find the short vector such that f times t is equal to 0. D is going to be our signature. In order to verify, you have three things that you need to check. You check the signature is short, you check that it is non-zero, and you need to check that when you multiply it with this f function, you get 0. And the dimensions again, but no time to discuss them. So now, as I said, we want to encrypt signatures and reason about their properties. We're going to start doing that. And as we progress, we're going to make observations. So on the left, we have Boolean signature, and now I just encrypted the signature D. So this is just like from the right side, I just copied what it means to encrypt it. And now this is the whole verification algorithm, but I don't have access to the signature anymore. But we still want to perform the check somehow. So what are we going to do? We are going to generate a non-interactive zero-knowledge proof. That's the idea. So we're going to need proofs for several things. We're going to need proofs for shortness. We're going to need proofs for the non-zero check. For the second part, what we're going to do is we're going to look at the encrypted signature. We're going to do some homomorphic evaluation. And then we're going to want that this homomorphic ciphertext encrypts 0. So we're going to have an ISIC for the homomorphic evaluation. But it seems like everything now is starting to tell us what kind of ISIC we want. So yeah, wanted a proof that something encrypted is short, non-zero, and an encryption of 0. And more abstractly, if I'm thinking of the encrypted signature being a short vector, I want to hide something short, so to smudge it. And despite the fact that it is hidden, I still want to be able to check somehow that whatever I smudged was initially short. And this is just a note, we are not using like flooding with like supernormally larger noise. I'm just trying to get that once I add the noise, it becomes statistically indistinguishable, and I don't know which element from the set I picked. It's going to become clear just now. So the first step is we're defining the structure, a notion that we call structure preserving sets, which is going to tell us where can we reason about what is inside the ciphertext and what can we sign. So here we're just going to say that there exists a noise distribution D for this set S, where we can hide the elements of S using smudging. So, and the second thing that I want is that we can still check after we smudged if they have the property that we wanted initially. So now I'm just plugging in what this means. I have S plus D, where S is an element from my set, and D is an element from the smudging set. And I want that this is statistically close to S prime plus D. And the same thing for for membership and non-membership. I want that when I look at my set S and I add the non-trivial elements of this D distribution, the intersection of this with the complement of S also smudged should be the empty set. So they don't intersect, and I don't have problems distinguishing from where they come. Obviously, this is a generalization. It's not going to be so simple. The second step is the reason that we have it is what I just said, that we want to check if the hidden signature is short. And this is where lattices are starting to make our life quite hard. And the first thing that I'm going to mention is that smudging actually will require rejection sampling. So the actual way it will look like there will be a success function, which will tell us for which we will have to do artificial aborts. And when we smudge on the left side, we are also going to fail sometimes on purpose. And the same on the right side is going to be a constant, and we're also going to fail. And all of these parameters are going to come from the rejection sample lemma by Lubachevsky. But the point is that we're actually abstracting it out, and we're giving the functionality of the set. So you don't have to worry about the rejection sampling lemma. And the second criterion that we want is that we can decide membership. So we can decide membership for the things that we smudge with. This is quite not obvious why, but yeah, we can talk about it afterwards. And I also should be able to determine whether whatever was smudged belongs to the set or not. We could also add that I want to be able to check membership in the set S, but that is not needed. We can work without it. And here I have this second relation that seems clean right now, but of course lattices are making our life hard again. And we're going to have a noise parameter, which is going to basically do fuzzy things around the balls. And that's why I put this approximation here. It's not defined, but if we started writing down parameters, we would be here forever. So some examples of what is a structure, like what kind of set satisfy these properties that I just mentioned, these two properties. For example, any coset of any additive subgroup of CP to the D satisfies this. Any singleton set, so set of just one element. Very useful for us would be sets where all the elements in the set are close to each other. So if you take any element from the set to subtract another one, they should be in a ball that's centered around 0. And yeah, so meaning that the vectors are close to each other. And also very useful would be the Cartesian product for two structure preserving sets is also structure preserving. And this would be useful because sometimes it will allow us to decompose our proof into multiple checks and then combine them at the end. Okay, so let's go back to the signature and try to abstract out what do we need. So basically, just a recap, we want that the sigma belongs to structure preserving set of short vectors, and we're checking this linear relation on sigma. And we're checking that this belongs to a structure preserving set with the singleton. So now I'm already expressing the verification algorithm in this language of structure preserving sets. And I'm going to ignore the non-zero check because that is quite hard. It's going to make my life hard. So we're ignoring it for now. And now I can express that again. I can, instead of saying that sigma is short, I'm just going to see this as a function that depends on the verification key and then the message, because I'm trying to get to the most general thing that I can achieve. So it's just an identity function, and I'm checking that this identity function belongs to the ball of short vectors. At the same time, I'm checking that when I take the signature and I'm applying the function that's just a linear function of the matrix F, the result will belong to the set that only has 0 inside. And this is just like another way of expressing what's happening here. And this is just like what I just said, written again. Basically, I'm saying that now a signature is structure preserving if I can write, I'm expressing the verification algorithm as the existence of a function that only depends on the verification key and of the message, which applied on the signature belongs to the structure preserving set. So we have that one. In the one in the paper is more general because in the application, we also need to cover strongly unforgeable schemes. And then they have a different structure, but yeah, please take a look if you're curious. And all of this property can be applied to Boyan, can be applied to Ruckert scheme, and can also be applied to a new scheme that we introduced in the paper, which is just a modification of Ruckert with the delegation strategy of ABB10. Okay, and now we have our structure preserving sets, we have the signatures, and now we only need the encryption. So we're very close. Basically, so this is a recap of regular encryption. I want to be able to, so I'm going to go fast. I want to be able to re-express encryption in terms of a single matrix. And the encryption algorithm is going to be, we're going to have linear encoding for the message, which is just like a way to help us with the rounding process and potentially to encode more than just bits. And then the randomness is just going to be, this is going to be such a preserving set soon. I'm going to add it on the slide. And the ciphertext will just be something of the form matrix times the randomness plus the encoding of the message. And this is why it's nice, because now I have this randomness here. I know it has structure preserving set, and it's really going to play well with what I need as a witness to my NISIC in the next steps. So here I'm just like confirming that the definition I just wrote makes sense. We can really rewrite regev like this. Basically, I already mentioned this, but I want that the randomness belongs to a structure preserving set. And this will also model things like Gaussian noise, like in dual regev. And so I don't want to limit myself to just things of this form. I want to have something general that covers as much as possible. I want to say everything, but and the fact that this encoding here is homomorphic, this would allow us to do homomorphic operations, which is what we need in order to perform those more complicated checks where I have a matrix times the signature. And the actual definition, I'm oversimplifying a lot, but the actual definition will also have a lot of noise properties. And this is on the right side, this is basically now the definition for the structure preserving encryption. It's just something of the form B times X plus this encoding of the message where R belongs to the structure preserving set. So let's go back to what we wanted to do. We have our encryption of the signature, which now is expressed in this language. And now I know that the verification basically means applying these functions. I can now apply them homomorphically on the encrypted signature. This homomorphism of G allows me to basically push the verification function inside. So now it's just next to D. And now I just need a way to check that whatever is inside the encryption belongs to the structure preserving set. So how to do this, and this is what we're going to discuss now. Basically, this is where the NISIC will come from. The NISIC is really going to be about the language that says what I'm encrypting belongs to the structure preserving set. And this is just restating that. And in order to construct this, we're going to rely on a schema protocol of Libert et al. And also on his transformations to compile the schema protocol into NISIC. He uses CI hashing for NC1 circuits. They use CI hashing for NC1 circuits, sorry. And we're going to use the same. And we're going to have security in the standard model. So yeah, this is just a recap now. We have the NISIC proof. I don't have time to go into how the NISIC works. Obviously, but you can look at the paper for that. And let's get closer to the conclusion. So we have seen how we can prove that the ciphertext encrypts a valid signature. And the fact that the signature signs a valid ciphertext, now we know how to do this because we know how to prove that the ciphertext encodes the actual correct value that is inside the structure preserving set. And I'm going to talk a bit about the application. So application is the verifiable encrypted signatures. We want to prove that the signature is valid without revealing it. And our construction in the paper is going to be the most efficient one in the standard model that we know. So the application is Alice wants to talk to Bob. They want to sign a contract. But if they did a simple thing where Alice just signs it, sends it to Bob, and Bob replies with it, with the signature, then Bob has a lot of attacks possible. He could refuse to sign and then just forward the signature to a third party to negotiate. He could impersonate Alice to another party. So that's bad. We want something more. We are not going to be able, with this construction that I mentioned here, to fix this problem, but we're going to fix the second problem. So basically, what you're going to do, you're going to encrypt the signature of Alice instead of sending it. You're going to make a NISIC proof that it is valid. Bob is going to reply with the same thing if the proof verifies. And this encryption is computed with the encryption of an authority, a third party that only has to put out PK and SK. And then Alice, once it receives this encryption of the signature from Bob, it replies it to her signature, and it's getting the final signature from Bob. So basically, if at some point one of them tries to cheat, like let's say Bob here, then Alice is going to talk to the authority and say, please decrypt the ciphertext, tell me what the signature is. And the authority will intervene, and because of the soundness of the NISIC, Alice is going to get the signed contract. So almost done. The contributions are, we propose a unifying framework for structure preserving cryptography for lattices. So these are the signatures we covered, the encryption. We have dual regga, we have GSW, and on the signature side, Boyan, Ruckert, and this modification of Ruckert with ABP delegation. The NISIC is based on a protocol by Libert et al. And we also, in the paper, show how to apply this to verifiable encrypted signatures. The proof has some new technical details, and is currently the most efficient lattice VS, the standard model. So one open problem to finish. There is this small problem. There is this problem here that Boyan signature, this non-zero check that I kept mentioning, that it's quite hard, actually makes things difficult for us. It makes so that like Boyan's signature is not really compatible with Reggae and GPV because this non-zero check is actually MC1 circuit. So it really doesn't fit into these two guys because it really has they only have like linearity. Yeah, and that's it. I guess another open problem would be to extend this to more complex primitives, and we think that is possible. Thank you for your attention.
Thank you. Okay, you mentioned there are other applications as well. You also have some on the motivation sides, right? Like, are there any problems you would run into? Have you thought about this already, or like, do you need lists for like different?
Yeah, that's a good question. So basically, we are optimistic about these ones. Can I have them?
Oh, yes.
Yeah, so we are optimistic about the group signatures and e-signatures. On the other hand, delegatable anonymous credentials really are far more complicated. Here we need the really strong properties from the NISIC, and also it's, if I remember correctly, they are bounded. And at some point with lattices, we really run into the noise problem, and we're not going to be able to replicate the same thing. Also, I think if I remember correctly, these delegatable anonymous credentials use the fact that the Grotz-Sahai NISIC itself is homomorphic. So the proofs are homomorphic, you can combine them. But that is extremely hard to do with our current NISIC, because our current NISIC uses a correlation tractable hash function, which is completely not homomorphic. So an open problem would be, for example, designing a correlation tractable hash function that has homomorphism. And that would really enable this segment.
Right. Thank you. Let's focus on threshold structure preserving signatures, strong interlevel security and the standard assumptions by Catherine Dumitro, Sayan Mukherjee, Madi Sedagat, Daniel Slamani, and Jenny Tomi, and Dennis Stuff.
Hi. So this is a work on threshold structure preserving signatures, strong and adaptive security under standard assumptions. This is Joshua, Katrina Mitrokotsa, Sayan, then Mahdi, Daniel, and myself. So this will be the outline of the talk. We'll go through the notations, definition, and then we see the construction, and then we go through the proof. So what is structure preserving signature scheme? So structure preserving signature scheme is a signature scheme, but the message and signature both are base group elements, and the verification has uses only group membership check and pair productivation. In a non-interactive threshold signature scheme, there are n signers with a threshold T, and the signers can generate partial signatures on message M. And there is a public algorithm that takes these partial signatures and generate a valid signature. A signature is said to be a valid signature if there were threshold number of signers who signed the message. Since the process of signing is distributed, it can be useful in decentralized web. So our goal is to construct a threshold structure preserving signature scheme, ideally in standard model under standard assumptions, and which allows adaptive corruptions of the signers. So there is only one work currently, which is by Kreitz et al., who proposed it in AsiaCrypt. So in their construction, they have a restricted message space, specifically indexed Diffie-Hellman message space. And the security is proven in algebraic group model and under random variable model assumption. And this is also proven under interactive assumptions. Interactive assumption named generalized Poinsot-Sanders tree assumption. And this is also secured only in the weaker model where there are no adaptive corruption, as well as there are no partial oracles given to the challenged message. So these are the notations. So we use a bilinear pairing group with groups G1, G2, and GT, and G1, G2 are the elements corresponding to the groups G1 and G2. And we use this notation where G to the power A is denoted by A in square bracket, and this can be generalized to matrices as well. So the hardness assumptions we use are matrix Diffie-Hellman assumption and kernel Diffie-Hellman assumption. So the matrix Diffie-Hellman assumption states that given matrix A and a hidden vector S, it is hard for an adversary to distinguish the vector AS from a uniformly random vector. So in a kernel Diffie-Hellman assumption, given a matrix A, it is hard for an adversary to compute or guess a vector S which is non-zero, and in such a way that AS is equal to 0. So now we will see the definition of the threshold subscription signature scheme. So there is a setup algorithm which takes in security parameters and output public parameters. The key generation algorithm takes public parameters, the number of signers N and the threshold T, and output public key secret key pairs of all the signers and their public key. The partial signing algorithm takes in public parameters, the signing key corresponding to that signer and the message, and output partial signature sigma I. And the partial verification algorithm takes in public parameters, the public key corresponding to the user and the message, and the partial signature, and outputs if it's 0 or 1, which is basically say that if it's a valid partial signature or not. And the combined sign algorithm is a public algorithm which takes in public parameters and a set T and the corresponding threshold, corresponding partial signatures, and output a signature sigma. And the verify algorithm takes in public parameters, public key, message, and signature, and output it's 0 or 1, which is either valid or invalid signature. So for correctness, we basically say that for all public parameters, for all valid secret and public key pairs, for all messages, if we have a partial, if we have a threshold number of partial signatures and then we combine them together, then it will be the verification holds. So now we actually defined several security definitions. So the first one is the weakest variant, which does not allow any adaptive corruptions. And also the adversary cannot make a signature or any signature oracle queries on a message, challenge message M star. So we will denote it as TSU of 0. So in this experiment, the setup algorithm outputs public parameters, and the adversary will output the number of signers N, the threshold T, and the corrupt set S. So since it's a threshold scheme, the number of corrupt signers should always be less than T. Otherwise, there would be trivial signature is possible. So in the key generation algorithm takes in public parameters, the number of signers N, the threshold T, and outputs the verification key and signing key for all the signers. And the adversary gets the signing keys corresponding to the corrupt set and all the public parameters. And adversary is also given a partial signing oracle. So adversary can query on messages and get back partial signatures. And by the end, the adversary outputs a message M star and the signature sigma star. The verification for an adversary to win, the verification should hold, and the message M star should never be queried to the partial signing oracle. So we want the adversary to be winning with negligible probability. So the next stronger variant is allows the adversary to make a limited number of signing oracle queries. So here the adversary wins if the number of oracle queries along with the corrupt set is less than T. So that means that the adversary can always make generate partial signatures on corrupt parties. So we need to limit it such a way that the trivial attack is not possible. So now we leave it.
Thank you, Jenny, for the introduction and some description. So she has already introduced you guys to TSUF0 and TSUF1. So these notions are actually defined by Bellare in 2022 in crypto. So we are just taking the definitions and trying to get a structure determining threshold signature that achieves the highest form of security that is there for the non-interactive signature threshold signature scheme. So TSUF1 is sort of the non-adaptive secure security model, and one can actually incorporate the corruption oracles, like adversary can make certain corruption queries and corrupt certain partial signers, and that actually gives us something called adaptive TSUF1 security model. And in this work, we have actually got a construction that is secure in this adaptive TSUF1 security, and that thereby this is sort of the strongest security available for a adaptive non-interactive signature, non-interactive threshold signature with adaptive corruption. So, okay, let's understand what exactly we want. So let's say this is the setting. So there are n parties and T is the threshold. So we are assuming that if there are 5 signers or 5 partial signers or more than that, in that case, we can reconstruct the signature. So so in this case, consider the adversary has corrupted user number 7 and 8. So the table is more or less self-explanatory. So 1 to 8 are the users, the partial signers, and the message M1 to MQ are all the message queries. Let's assume now adversary, let's assume it has corrupted already the user 7 and 8. That means secret key for 7 and secret key for 8 will be available with the adversary. Now, if the adversary gets partial signatures on sigma 4, sigma 5, and sigma 6 with respect to message 1, that means it is having 2 secret keys and 3 partial signatures. It is having and the threshold is 5 only, so it can reconstruct the signature completely, right? So therefore, it can easily sort of forge. So that should be a trivial goal. So we have to define the non-trivial goals, and here the goal will be the forged message should not be a part of M2 to MQ, because we have already assumed that M1 is already forged. So M star should be among M2 to MQ, and if we assume that there is certain M star that is MI, so M star either will be outside this M2 to MQ or it will be part of M2 to MQ. Now, if there are 2 different notions, like TSUF1 actually captures the first one, 2.1, and TSUF adaptive TSUF1 is actually 2.2. So we will focus on 2.2. In the paper, we have given proof for all of them. So maybe you guys take a look, but I will focus on the most interesting one, which is TSUF adaptive TSUF1, which is 2.2 secretive notion here. Okay. So now consider forging sigma 6i is hard. So let's assume we have a UFCMA secured signature sigma, and we are running them parallelly for each individual users. So there are 8 users and we are running them parallelly. And in that case, forging sigma 6i will be hard, even if all the other signatures are given on different messages. So what I'm saying, given if this sigma is UFCMA secure, in that case, producing this or forging this will be hard for an adversary, even if that adversary is given all the signatures on that on different messages. Now, what if adversary gets this signature? Let's say sigma 4i and sigma 5i. So that means adversary gets signature on message I with respect to secret key SK4 and SK5. So does it leak some information regarding with respect to the total signature, total secret key or total master secret key? Or yeah, so that is the concerning thing, and we wanted to take a look at that. So our goal is to prove, even if the adversary has so many information about the partial signatures and the secret keys, it will still be hard for the adversary to produce a forgery on sigma 6i. So that is our goal. Okay, and for that we take a look at a seminal work by Kills, Pan, and we. Yesterday there was a paper already who already used this structure, so I'm not going to describe the structure much, but I will just tell you 1 or 2 things. So KPW rejects same tau for different messages. So in the proof of KPW, if you have same tau used for different messages, so for M1 and M2 using same tau, that's not allowed. And another thing is that KPW is not a strong UFCMA secure. That means you are not allowed to make queries on the signature queries on the forged message, right? However, in our case, we have to allow that, and that is where our novelty lies. So what we do, we notice that what if we secret share the K that is present in KPW among all the parties. So then what happens? Each party will have a secret share of the key, which is kj, and each partial signature, and we also allow each partial signature. For each partial signature, each party can choose its own randomness. So basically, in our case, the partial signature will look like this. Where notice index j is present in k and r. However, message and tau are indexed by same I, not j. Okay. Now, the benefit of this structure is that if we have a satisfying, if we have a set which have more than t number of users, in that case, we can actually do a linear recombination of the partial signatures to construct the complete signature, provided the partial signatures of MIs are using same tau I, and the proof should work if tau, different taus. So for different messages, we have used different tau, and this from this we can actually see that there is a nice message to tau. So if we assume there is an injective mapping between message and tau space, in that case probably we can do that, and that is what we do. So our achievement, I would say, even though the structure looks quite complicated, our achievement, our sole achievement, I would say, is the defining tau in terms of a hash function. We used a collision resistant hash function over there that ensures that the message and the tau are connected in an injective manner, and that actually allows us to do the linear recombination quite easily. Not only that, the proof of KPW can be modified just a bit to work in our situation as well. So we will just see a proof intuition. So let's say each party has a secret key kj. So each party j has a secret key kj. Now in KPW's proof, they used some notion of residual entropy. So in their proof, even after partial signatures on different messages, they could ensure that that kj. So from KPW, we can actually argue that kj will still have some residual entropy, even if we have given some partial signatures with respect to user j. Then we also use semi-secret sharing, which almost very naturally comes to our scheme. So semi-secret sharing is an information theoretically secure, and we use the effect of semi-secret sharing on residual entropy, and this actually ensures that even if we have leaked some of the k, so let's say k4, k5, small k, so residual entropy of k4, k5, k7, and k8 are leaked, but still semi-secret sharing ensures that k6 will be hidden because the threshold we are considering to be 5 users, right? So therefore, this notion of residual entropy we can use to ensure that kj, in particular k6 here, can be hidden, and even this also holds even when we are leaking kj adaptively. So we can handle adaptive query. And another crucial point here I should mention is that KPW allows the reduction to no k's in plane, and therefore we could also see that our reduction can also use those our reduction can sample those kjs, and it knows those secret keys, and therefore handling the adaptive corruptions are much more easier for us. And yeah, that is the proof intuition, and I will just glance through the hybrid argument. So we have given a hybrid argument, we have defined a couple of games, and we proved each of the consecutive games to be computationally indistinguishable. And yeah, and the main crucial achievement in our work is game 5 and game 6, where we had to ensure that even if we are getting many partial signatures and we are getting many adaptive corruption queries, but still we could manage the indistinguishability and the final game having zero advantage. If we can show them, okay, show those argument, okay. And so I am going to summarize the work we have done. So this is the first adaptively secure threshold structure preserving construction. It has competitive efficiency with the previous one that was given in AsiaCrypt 23. Then this is the first standard model construction, and we have proved it secure under standard matrix Diffie-Hellman and kernel Diffie-Hellman assumptions. And thank you for your attention. If you have any question, we would be happy to answer.
Thank you. Are there any questions?
What is the state of the art of? This is the only one, I would say. So we are the state of the art, it seems. Yes. There was another work, just the previous one that I have referred, that we have referred here from AsiaCrypt 23. They did not consider adaptive corruptions. So they proved their security in the weakest form of so they proved the security in TSUF0, which is the weakest form of non-interactive non-interactive threshold signature. We could actually improve the security, achieve much more stronger security in the standard model. So yeah, I'm not sure if that answered your question. Right. Okay. Thank you.